So in the last class, we did a few things that were the beginning point on our work on energy conservation. So let me just firstly just recap some of the things we did in the last class. First thing that we did was introduced a concept of work or work done. And the work done or work is something that's done by forces. So we say that forces do work. When forces act, those forces do work. And we defined the relationship between the force that is acting and the work that that force does. And actually, that was that little equation here. Oh, this is not. This guy here. We went on to discover that the network that forces do, well, that changes the kinetic energy. Okay, so if forces do some network on some object or body or particle, that changes the kinetic energy, correspondingly changes the kinetic energy of that body or particle. So that led us to a second new quantity, which is kinetic energy, energy by virtue of motion, energy by virtue of movement. And we were able to write down an equation for the kinetic energy of a moving object. Maybe it's an elephant, maybe it's a mouse, but that kinetic energy depends on the mass of the object and the speed of the object. And as I say, it's really was our first look or our first glimpse into what is kind of like this hidden garden of energy, different types of energy, and conservation of energy that lies lies beneath forces and how forces interact. And we're going to continue to work on exploring this sort of hidden garden of energy and energy conservation today. So there's two main things I want to do today. Here they are. One is to introduce some different types of energy. One will be, well, we started to talk about kinetic energy, but we're going to say more about that. Another one will be what we call gravitational potential energy. We'll say something about that. And then finally, we're going to talk about spring potential energy. So these are three types, three forms, three brands of energy that we'll talk about in today's class. And that's really going to be our first topic. And then a second topic here is to talk about energy conservation, the idea or the concept of energy conservation. And we're going to apply energy conservation to examples that involve kinetic energies and gravitational potential energy and spring potential energy, etc. And so that's really this energy conservation is our second topic for today. Okay, so let me move on with that. So let's start with kinetic energy. And as I say, the important thing about this is a type of energy. This is a brand of energy, a form of energy that is associated with movement, that is by virtue of motion. And just to give you an idea, right? You know, if you had a fast-moving elephant, that would correspond to a object or a body with lots of kinetic energy. If you had a slow-moving beetle, that corresponds to an object or a body with just very little kinetic energy. So it's a characteristic of the body and of the motion of the body. So this slide is meant to show how we're going to move from our original force perspective that we were talking about before test one to this new energy perspective that we're discussing post test one. And so on this slide, I pictured a situation. We've met it before, but we're going to meet it again. And we met it before in the sort of force perspective. We're meeting it again in the energy perspective. So on this slide, I'm imagining some block. Here it is in this nice orange color, or ugly orange color. And here it is sliding across this table or sliding across this floor. And we see the block move from left to right. Here's the displacement. And we see the block increasing or decreasing or changing its speed. And as I say, we previously analyzed this situation from a force perspective. Oops, sorry. I gotta get the pen working again. We previously analyzed this from a force perspective, in which we said that the net force on the object determines, through Newton's second law, the change in velocity of the object. And so that was one way of understanding the motion of the body, by understanding how forces influence the motion through Newton's second law. They cause acceleration. But now we're turning to a second way of analyzing the motion of the block across the table. And in this way of thinking about it, we think about the net work that's done on the object. So that's this this symbol here. That net work that's acting on the object changes the kinetic energy of the object. And that's in accord with the work-energy relationship, that the net work on the object is equal to the change in kinetic energy. So these are the two perspectives, the old one, the force one, and the new one, the energy one. And in the old one, right, it's forces that created a change in velocity. In the new one, it's work that creates a change in kinetic energy. And as I say, in some problems, it's handy to work with forces. It's more natural to work with forces to understand a problem. Other problems, it's handier or more helpful to work with the work that's done to understand a problem. And so that's why we learn both of these perspectives. And the other reason we learn both of these perspectives is to give us kind of a deeper, a fuller understanding of motion and the origins, the nature of motion. Okay, so let me go on to the next slide. Clear all this. And on this side, I'm just going to make a few comments about this new energy perspective. So a few key comments about it. So the first one here that I've written down, gosh. The first one that I've written, here it is that network done. What network done is the net energy transferred, or the net energy moved, the net energy that flows to an object by the action of the net force, by the action of the total force on that object, or the summed force on that object. So, you know, when we talk about net work done, it's really a shorthand for saying the net energy that gets transferred. And it's the net energy that gets transferred by the net force that's acting. And so, you know, forces are, one thing they're doing is transferring energy. and the work done is the measure of that energy that they're transferring. The second point here is that net work that's done, or that net energy that's transferred, that goes into changing, ordering, increasing, decreasing the kinetic energy of the object. So when you transfer energy, you're not going to destroy any of that energy. You're not going to create any new energy. You just transfer it to that object. And so network is transfer of energy. It's not loss or creation of energy. It's just the transfer of energy. So that's the second point. Third point, in green here, is that that transfer of energy can be positive. That work done can be positive. That if it's positive, it means that the kinetic energy of the object would have been increased, would have grown. That net work done can also be negative. If it's negative, it means that the kinetic energy of the object is going to be decreased or shrunk. And it can also be that the net work done on an object by the various forces acting, it could be that that's zero, in which case the kinetic energy is neither increased or decreased, it's unchanged. So all of those are possibilities. Okay, so now I want to mention that perspective. I want to apply that perspective, this energy perspective, to a problem. So let me go on to the next slide. Okay, so in this example, we've got an athletic raccoon who's doing a chin-up. It's 40, 50 years since I've been capable of that, but the raccoon is capable of doing a chin-up. And we're told a few facts about it. So one thing we're told about is that the raccoon's weight, excluding the raccoon's arms, is 175 newtons. Now, it's the raccoon's weight excluding the raccoon's arms because his arms are lifting his body. So the weight the raccoon's arms are lifting is his weight less the weight of his arms. So that's why it's 175 newtons. We're told that the lift, the distance the raccoon lifts his body, his torso, is 16 centimeters, 0.16 meters. And we're told that the raccoon lifts his body, if you look on the left and right, his little paws there, kind of cute, they're applying 155 Newton force each on his torso. And what we've got to figure out, so imagine you're the raccoon, you're just doing this chin up, your torso weighs 175 newtons, you're applying with your left and right hands 155 Newton forces to lift yourself up. But if you started from rest, after you've pulled yourself up, that's 16 centimeters, that 0.16 meters, how fast are you going? That's an interesting question. So let's see if we can solve that. And we're going to do it, so say, not from that old-fashioned fuddy-duddy force perspective, but now we're going to do it from this new, modern, exciting energy perspective. And specifically, what I'm going to do is figure out the work done on the raccoon's body. And by figuring out the work done on the raccoon's body, we can use the work-energy relation to find the changing kinetic energy, or the final speed of the raccoon. We're going to focus on the final speed. So let's do that. And there's really 2 steps to the calculation. But as always, I want to start over here on the left-hand side with my picture of the situation. So I drew a picture of the raccoon quickly, and then I added to the picture the various forces that are acting on the raccoon's body. So one force is the weight of his body, is force of gravity. So we were told that that's 175 newtons. And then the other two forces are his little arms here. Look, they're pulling up on his torso. And we were told those two, they each exert a force of 155 newtons. So there's 155 newtons on the left and 155 newtons on the right. So those are the various forces that are acting. And those forces would influence his motion. They would cause him to move upwards. We're going to solve the problem, though, from the work perspective. We're going to think about the work that's done by those forces, calculate the work that's done by those forces, and then from that work that's done by those forces, we're going to figure out the change in kinetic energy and the final speed. So let's do that. So then I'll go over here to this starting point. The net work that's done on the raccoon's body, which is the work that's related to the kinetic energy change. That net work is the sum of the works that are done by the individual forces. And there's three forces in my picture. So, you know, there's the force of gravity here in orange. And then in this nice magenta, there's these amounts of work done by the pull of the left and right paws of the raccoon. And so that's the starting point, that we've got these three forces doing three amounts of work. Let's add them up. The amount of work that's done by a force, well, that's the size of the force times the displacement times the cosine of the angle between the motion and the force. And so I then fill that in. So for gravity, it's this little guy here. Fg is the force of gravity. Delta x is the displacement of the raccoon. And well, it would be cosine of the angle between the gravitational force and the motion. The motion is up, the gravitational force is down. So that's 180 degrees between the gravitational force and the motion. Cosine of 180 degrees is -1. So that's where the -1 came from. Then I've got two more forces. The two paws of the raccoon pulling up, and the work they do is the size of their force, size of the displacement times the cosine of the angle between the force vector and the displacement vector. The force vector in this case and the displacement vector are upwards. They're both upwards, 0 degrees between those. And so it's just force times distance. The cosine of 0 degrees is 1. Okay, so that's good. I then just filled in the numbers, right? Because I know the gravitational force. I know the force from the raccoon's paws on the left and right, and I know the displacement. So I filled in the numbers, and I added them all up, and that gives me the net work that is done, which is, by the way, the change in kinetic energy. So here's the final minus the initial kinetic energy, which in this case is just the final kinetic energy because there was no initial kinetic energy. And it comes out to be just under 22 joules. So that was a simple calculation from energy work perspective of the network that's done and the change in the kinetic energy. And now we know the network that's done, or the change in the kinetic energy, or the final kinetic energy. We can just use our expression for kinetic energy, this new form, this new brand of energy we just met, and rearrange it to solve for V. So I multiplied by 2, I divided by the mass, I took the square root, and this is the equation for the velocity, the speed, in terms of the kinetic energy. And we know the kinetic energy change. We know the final kinetic energy. It's the work that was done, the net work that was done, and so we can find the speed. And so this final step here, I just fill in the 21.6 joules of work that those little paws and that force of gravity did overall on the raccoon. I fill in the mass of the raccoon. I knew it because I was told the weight of the raccoon over here. And I solve for the speed. And here's the speed, 1.6 meters per second. And so I would encourage you to step back from that problem and think about what we just did. We solved a problem of, forces creating motion, forces influencing motion, but we didn't solve it by the old method of, figuring the forces and figuring through Newton's second law the acceleration. Rather, we solved it by figuring the work the forces do, and then using the work-energy relation to find the final speed. So it is a different route. It is a different way of solving that problem. Okay, that was fun. It's always good working with animals, I guess, is the thing, even in problems. Let's get rid of all that, and let's try and move on, if I can, to the next form of energy that I want to talk about. And this is gravitational potential energy. And, this is like kinetic energy was energy associated with motion or by virtue of motion. Gravitational potential energy is associated with interactions, gravity interactions here. It's energy by virtue of an interaction, a gravitational interaction here. Look, you already know from your everyday lives, everyday experience, something about gravitational potential energy. In this picture, right, a brick on the top of a skyscraper, that has a lot of gravitational potential energy. If it falls off, that brick can do a lot of damage when it hits the ground. So that's an example of, like the elephant. The running elephant had a lot of kinetic energy. Well, this falling brick was a store of lots of gravitational potential energy. Okay, so I want you to imagine this situation, and I want to use this situation to introduce gravitational potential energy as a concept, and secondly, the equation for gravitational potential energy in terms of the properties of the object and the location of the object. So what we're considering in this little sketch is a brick that is falling, say, from the skyscraper to the floor. And so here's the brick at the top of the skyscraper, and here's the brick just before it hits the floor. And this is the initial height, y subscript I for initial. This is the final height, y subscript f for final. And this is some initial velocity, vi, some final velocity, vf. And we know, right, as the brick falls down, it's going to get faster, so the velocity is going to increase. So vf is going to be bigger than vi, and the associated kinetic energy, that's going to increase too. So the final kinetic energy, KEF, is going to be greater than this initial kinetic energy. And what we want to add to this picture is the gravitational potential energy. Here's the initial gravitational potential energy, and here's the final gravitational potential energy. And again, we're going to be looking at this example from a fresh, a new, a modern perspective. Rather than looking at it from the force perspective, Newton's second law, we're going to be looking at it from energy perspective and energy concepts. Okay, so the key thing then is the idea that the falling brick is acquiring kinetic energy. So the kinetic energy that I've pictured here, this kinetic energy is increasing. as it falls. And the question is, where does that kinetic energy come from? And the answer is it comes from the stored gravitational potential energy. That's correspondingly decreasing. So in the energy perspective of the falling brick, acquiring kinetic energy, it's acquiring kinetic energy because it's giving up, losing gravitational potential energy. Overall, energy is just being transferred. Energy is being moved around from one form, the gravitational potential energy of the brick at the top of the skyscraper, to kinetic energy that the brick has when it strikes the ground at the base of the skyscraper. And that energy is transferred from kinetic energy, is transferred from gravitational potential energy into kinetic energy by the action of the gravitational force, by specifically the work that is done by the gravitational force. So the force and the work, these are the agents of transferring that energy from initially being gravitational energy to finally being kinetic energy. And so that's the energy perspective of what's happening here. Now, with that perspective, we're going to associate a couple of equations. The first one is this concept that gravitational force is doing some work. So it's a force that's acting as the brick moves. So we'll be doing some work. I've called that work the gravitational work here. And the amount of gravitational work that's done is the negative change in the gravitational potential energy. And what that means is that whatever work that gravity does on the brick, whatever amount of energy it transfers to the brick, is taking that, is kind of stealing that energy from the reserve, the store of gravitational potential energy. And so that's the reason for the minus sign here. So this equation upstairs here, this idea, this concept upstairs here is simply saying that when that gravitational force is doing work, is transferring energy from a store of what we call gravitational potential energy, and is transferring it to the motion, the kinetic energy of the object. And that gravitational potential energy has an equation for it, just like the kinetic energy had an equation for it. And when we figured out the equation for the kinetic energy, we got it from the expression, the formula for work done in terms of forces. You could do the same thing here, get the gravitational potential energy equation for the work done by gravitational forces. And I'm not going to do it, but it comes out to be this little formula here. And what you see is that m is the mass of the object, g is the acceleration of gravity, and y is the elevation of the object, the height of the object. And so you see in that formula for gravitational potential energy that the more massive the object is, the greater the gravitational potential energy. So if a mouse and an elephant jump off a skyscraper, right? The massive elephant has more gravitational potential energy to be released than the light mouse. Secondly, it says that it depends on the elevation or the height of the object. So, you know, an elephant and a mouse jump off a tall building versus jump off a not very tall building. When they jump off the tall building, they've got lots more gravitational potential energy to release by virtue of their height. If they jump off, you know, a step, they've got very little gravitational potential energy to release by virtue of their height. And then finally, it also depends on the acceleration of gravity, g. That might not be surprising, right? If you go to the moon and jump off a building, you'll release less gravitational potential energy because there's less gravitational force, less gravitational acceleration on the moon. If you went to Jupiter, right? If you went to Jupiter and jumped off a 6-foot wall, you'd hurt yourself because there's much more gravitational potential energy to release because gravity is much stronger on Jupiter. the gravitational forces are much stronger on Jupiter. Anyway, so this is a summary of this new concept of gravitational potential energy. Let me clear that. I want to make a few remarks about it, and then we'll look at a problem. So, to summarize, some comments on this new concept term of gravitational potential energy. When a gravitational force does gravitational work, what that is transferring or transforming energy, and is transforming or transferring energy from a kind of store of gravitational potential energy. Gravitational work done is the negative change of the gravitational potential energy. What that means is, you know, when you pull gravitational potential energy out of the store of gravitational potential energy, you're not going to lose any energy. You're not going to gain energy. However many joules you transfer with the work done is the amount of joules that you lost in the gravitational potential energy store. A remark on this remark here. Oh, sorry. Gosh. A remark on the signs of changes in the gravitational potential energy. So if an object falls, it releases gravitational potential energy. And the gravitational force is doing positive gravitational work on the object. If the object is thrown into the air, is rising into the air, that's increasing the stored gravitational potential energy. And in that case, the gravitational force is doing negative work on the object. And it's also important, the last point on this slide, that gravitational potential energy is not just associated with the brick or not just associated with the Earth. It's really associated with the Earth-brick interaction. It's the two of them together and how close or far they are apart that's determining the gravitational potential energy that's stored. Okay, so let's look at now we've introduced that concept, let's look at an example and try and get a better feeling for it. So in this example, what have we got in this example? This is meant to be a roller coaster example, so that's always fun. And we're told that we've got a 80-kilogram roller coaster and it's sliding down a frictionless incline. And we've got to determine the work that's done by gravity now on the roller coaster as it goes from an initial height of 30 meters to a final height of 0 meters. And we've got to figure out the speed of the roller coaster. So this is a problem, again, we could have done this problem with that old-fashioned, fuddy-duddy force perspective. Now we're going to do it with this new, innovative, intriguing energy perspective. So, you know, this is a problem that can be solved by two perspectives. There's two ways of thinking about it. Forces creating motion, or work being done and increasing kinetic energy. And they both approaches, both methods give us insight into what's going on and what's happening in this particular example of a moving object. Okay, so the first thing I did was actually start with a force perspective and a force diagram of the roller coaster, because we're then going to use that to calculate the work that's done on the roller coaster and the final speed of the roller coaster. So I pictured here on this slide, I've pictured let me get the pen going. I pictured the incline, which the roller coaster is sliding down. Here's the roller coaster, it's 80 kilograms. And it starts at a initial height over here. This is 30 meters. And ends up a final height elevation of 0 meters. So the change in height is minus 30 meters here. And it starts with an initial velocity of 0. We were told it's initially at rest, and final velocity, we want to figure that out. So that's a picture of the problem. And then I added to the picture, you know, the various forces that are acting on the roller coaster. In this case, there are two forces, gravity and normal force. This was a frictionless incline, so no friction force. Gravity in magenta here, that's acting vertically downwards. That's the gravitational force due to the object's mass. And then the normal force in blue here, that's preventing the roller coaster from falling through the coaster itself. Okay, let me go on to the next slide. Let me clear that. And so let's go ahead and do the calculation. We're going to calculate the final speed by calculating the gravitational work that's done. So again, this is this new work energy perspective, not this old force acceleration perspective. So what's the gravitational work that's done? Oh gosh. Let me get the pen going. Well, here's my gravitational work done. The little g means the work done by the gravitational force. And as we described, the work that's done by gravity corresponds to a change in stored gravitational potential energy. That's this little expression here. And the change in gravitational potential energy is the final gravitational potential energy minus the initial gravitational potential energy. So the initial gravitational potential energy is the energy at that height of 30 meters. The final gravitational potential energy is the gravitational potential energy at the height of 0 meters. So I've filled in those quantities there. Okay, well, if I look at this expression for the work that's done, using our notion of gravitational potential energy and our understanding of how it depends on the mass of the object, the elevation of the object, we got a little equation where everything inside it we know. We know the mass of the roller coaster is 80 kilograms. We know the acceleration on Earth, gravity, is 9.8 meters per second squared. We know the initial and final heights of the roller coaster. And so if we plug all these numbers in, 80 times 9.8 times 30, that comes out to be this large number of joules here. 23,500 joules of work is done by gravity on the car. And so step back from that before we do the next part of the problem. What we just figured out in sliding down this frictionless incline from an initial height of 30 meters to a final height of elevation of 0 meters, the gravitational force is doing some work, and the amount of work that gets done is 23,500 joules. So the store of gravitational potential energy, the store associated with the roller coaster and the Earth, that's gone down by 23,500 joules. And that 23,500 joules of gravitational potential energy has been transferred, in this case, to the kinetic energy of the now fast moving car. And so now we're going to use the work energy relation to find out that final kinetic energy, find out that final speed. And so that's what I'm doing in the second part of the problem. The work energy relation, if you remember, says that the net work done on the cart is the change in kinetic energy. In this case, there's gravitational work that's done on the cart, but because the normal force and the motion of the cart are at right angles to one another, 90 degrees to one another, there's no work done by the normal force. Forces at right angles to motion do no work, and so that's an example of that. So actually the net force, the net work that's done on the cart is the gravitational work that's done in the car. It does all the work on the car, all the non-zero work on the car, and it's it that changes the kinetic energy, i.e. it that's responsible for the final kinetic energy of 1/2 mv squared, because the initial kinetic energy was 0. So all we have to do now is rearrange this work energy relation here. Rearrange it for the final speed, the thing that we want to figure out, by multiplying by 2, dividing by the mass, and taking the square root, in terms of that work done by the gravitational force. That's the WG here. And so I get this little equation here, and I substitute in the work that was done by the gravitational force, 23,500 joules, the mass of the car that's sliding down the roller coaster, and here's our final result for the speed, 24 meters per second. So again, stepping back, it's a problem we could have solved by force perspective. We've solved it here from energy perspective, and it gives us a new way of thinking about what's going on, the flow of energy from gravitational potential energy into kinetic energy. I wanted to show, just show a little demonstration or a little video of what's going on in this problem. Is the flow of energy between potential energy and kinetic energy, between gravitational potential energy and kinetic energy. And that flow of energy is due to the action of forces doing work. So they cause the energy to be exchanged or to flow around. And a roller coaster is a great example of this sort of flow of energy between gravitational potential energy and kinetic energy. And so I just want to show, partly for a break, a roller coaster video. And when we watch it, let's think about the flow of kinetic and potential energy. So I'm going to stop sharing this screen and share a different one over here. And so I hope you can see this. And we're gonna, let's take, I know, the whole class, all 163 of us. We're all gonna go on a roller coaster ride. I think we can all get on this one. Okay, well, that was fun. I hope nobody's got sick or anything. Let me go back to the slides. So the key thing about the roller coaster ride was, as you go up and down in the roller coaster, from an energy perspective, what we've been doing today is that you're transferring energy from kinetic energy to potential energy and vice versa. As you go downhill, the gravitational force is doing positive work, and you're losing potential energy, gaining kinetic energy. As you go uphill, the gravitational force is doing negative work, and you're losing kinetic energy, but storing more gravitational potential energy. And so that's the next time you go on a roller coaster, think through that. I mean, I don't want to ruin the experience for you, but I mean, it is kind of interesting. I want to move on to a third type of energy now, spring potential energy. So let me try and do that. I'm trying to get my annotation back, if you wonder what I'm doing. Okay, so here we are. Spring potential energy. So this is another type of energy associated with an interaction. It's another type of energy by virtue of an interaction. If you stretch a spring, if you compress a spring, you're interacting with the spring. And that interaction has an associated spring potential energy. And you probably know, if you stretch a spring a lot, right, or compress a spring a lot, that spring is storing and able to release a large amount of energy, can release a lot of energy. So springs, like gravity, involve interactions, gravitational interactions, spring interactions, and they store energy and can release energy. I'm just trying to get the chat back in case somebody says something. Okay, so let's talk about spring potential energy. The first thing I actually have to do is introduce the spring force. And here's the equation for the spring force. Oh, do that every time. I need to get the pen working. Here's the equation for the spring. Gosh. It's been a long day. One more time. Try. Here's the equation for the spring force in terms of what we call the spring constant. So let me explain this equation for the spring force. Then we can go on and worry about the work that's done by the spring force, the stored spring energy, the release of spring energy, et cetera, et cetera, et cetera. So here's a spring with a block on the end of the spring. And at this upper picture, the spring has its equilibrium length. That means, by that I mean it's neither stretched, we're not pulling it apart, or it's not compressed, we're not squeezing it together. If I were to compress the spring, that's the second picture here. So here I am compressing the spring. Look, the windings are getting closer. So I push the block on the spring towards the left by some distance x. The spring pushes back with a spring force that's this F of subscript S. And so that's the spring force. And that spring force grows with the amount that you compress the spring. firstly. And secondly, if you look at the direction, it's opposite to the direction of compression of the spring. And that's what the spring force equation says. The force that is produced by the spring is in proportion to the amount that you've compressed it, and it's opposite the direction of the compression. Look at the stretch case. Same law applies to that. If you stretch the spring, okay, so look here, I've got the block attached to the spring and I'm stretching the spring from the equilibrium length. So I'm moving the block and the spring towards the right in this case by some distance x. Stretching the spring also creates a spring force. Again, it pulls back in the opposite direction to which you've stretched it, and it pulls back with a strength that is in proportion to how much you stretch it. And that, again, is described by this, this spring force equation. And so that's how springs work. Inside the equation is a constant. That constant's called the spring constant, and it sets the scale for whether the spring is a strong spring or a weak spring. So if you've got a spring with a large spring constant, that's a strong spring. That is a spring that's tough to compress, tough to stretch, right? Such springs would be in the suspension of your car. They're pretty hard to stretch and compress. If you got a spring with a small spring constant, that's, that would be really easy to stretch and compress. So the spring constant of a spring sets the scale of the forces that the spring produces when you compress or stretch it. The spring equation for the force, that tells you how the force grows the more you stretch or compress, and how it goes away at the equilibrium length of the spring, where x is 0. So that's the law for the spring force. It came from a very famous physicist called Robert Hooke, who was around at the same time as Isaac Newton. And Robert Hooke came up with this law for how springs work. Kind of like Archimedes came up with a law for how levers work. And it's a very important equation. It can be applied to these sort of everyday springs or little atomic molecular springs even. We'll talk about that later in the course. Okay, anyway, that's enough detail on that. Let's clear. And let's go to the next slide. I'm capable, somehow not capable. Okay, here we are. So here I want to introduce the concept of spring potential energy. And in this picture, it's kind of meant to resemble that case where we dropped a brick from the skyscraper, which started out with lots of gravitational potential energy and turned it into kinetic energy. In this case, we're going to release a block on a compressed spring, and it's going to turn that spring potential energy into kinetic energy. And so that's what I'm picturing here. Sort of in the upper picture, get pen going. In this upper picture here, xi is the initial location, xf is the final location, vi is the initial speed, maybe it's at rest, vf is the final velocity here, final speed. We're imagining the spring is compressed in the upper picture and then released and expanded in the lower picture. What we know is that that will turn spring potential energy into kinetic energy, just like in the falling brick. Gravitational potential energy was turned into kinetic energy, and so that's the energy perspective on what's happening here. As the compressed spring expands, it turns that store of spring potential energy into kinetic energy by virtue of the fact that there's a spring force that does spring work. And that's the transfer of the energy. And with that idea go, just like gravitational potential energy, a pair of equations. So the basic concept is that when the spring force does work, so that's this WS here, which parallels the WG in the last example, that corresponds to a negative change in the spring potential energy. Like there was a negative change in the gravitational potential energy when you drop the brick. And just like for the falling brick, we have an equation for the gravitational potential energy that you can easily actually derive based on the relationship between the work and the force, the gravitational work and the gravitational force. In this case too, there's an equation for the spring potential energy that you can derive from the relationship between the work that's done by spring force and the force itself. Here's the equation for the spring potential energy. And you see in this equation, right, it depends on a couple of things that are interesting. It depends on how much you compress the spring, that's the X, or stretch the spring. So the more you compress or stretch, that will change the spring potential energy. And it depends on the spring constant, right? Whether you've got a spring that's easy or difficult to compress. It depends on that quantity too. Okay, so I want to move on to an example of spring potential energy. Clear that junk. Go to the next slide. Okay, first I want to make a couple of comments. So spring work done, again, just like gravitational work done, is energy being transferred. And it's being transferred, it's not being created out of nothing. Is being transferred from this reserve of spring potential energy by virtue of the fact you've compressed or stretched the spring. It's being transferred by the spring force. The spring force is doing work. So that's the first point. Second point is that, you know, in that process, there's no loss or gain of energy. Whatever spring potential energy you take out of the spring or put into the spring, there's a corresponding amount of work that's done by the spring force. So you never lose or gain energy in this. If the spring is compressed, that increases spring potential energy. And negative spring force work is done. But also if you stretch the spring, that also increases the spring potential energy. It stores more spring potential energy, and negative spring work is done. If you release a compressed spring or you release a stretched spring, in that case, positive spring force work is done and the spring potential energy decreases. So that's a little different from gravity, and it's because the gravitational potential energy just depended on the elevation, but the spring potential energy depends on the square of the compression or the stretch. So that's an important difference between spring potential energy and gravitational potential energy. Now let me go on to an example problem. But first I want to do a quiz. Okay, so if you compress a spring, if you double the compression of a spring, so that's doubling X, that measure of the compression of the spring, that actually stores 4 times as much potential energy. And you can see that in the equation for the spring energy, because it goes as the square of the compression of the spring. So if you double, you're going to store 4 times as much energy. If you triple, it's going to store 9 times as much energy. So the more and more you compress a spring is interesting, the much more energy you need to provide to store a spring potential energy. So it gets costlier and costlier and costlier to store spring potential energy as you compress the spring more and more and more. Okay. So let's end the class today with a example, illustration of spring potential energy and the work done by spring forces. So in this particular problem here, we're asked to imagine this situation in which we've got a spring, and we're told the spring constant is 500 newtons per meter, and it's compressed by 2 centimeters, 0.02 meters, and it's compressed with a block of 100 grams or 0.1 kilograms at rest on it. And so this is a situation where we're holding that block on the compressed spring, and then we're going to release the block. And we're going to figure out what speed the block acquires when the spring releases its spring potential energy, gives it up to the block's kinetic energy by exerting a force on the block, which does work on the block. And we're going to figure that speed of that resulting final speed of the block. So let's do that. Okay, so my first step was to actually sketch the forces. So think about the force perspective. And then I can worry about the work that's done by the various forces and the energy that gets transferred and how spring potential energy gets turned into kinetic energy. So if you look on this picture, I've got the block here, I've got the spring over here on the right. I've got a gravitational force that's acting on the block downwards. I got a normal force that's acting on the block upwards. And then I got a spring force that's acting on the block towards the left. Now, the gravitational force will do no work because it's perpendicular to the motion. The block can slide across the horizontal floor. The normal force will do no work because it's perpendicular to the motion. The block's going to slide across the floor. It's only the spring force that's going to do work on the block. And so the spring force in this case will be the net force in this case on the block. The spring work will be the net work on the block. So let's do the calculation then. So here's the calculation. First step in the, In the first step, I'm going to calculate the work that's done by the spring force. And then it'll be in the second step that I calculate the speed of the block itself. So there's 2 steps. I'm going to calculate the work that's done by the spring force because it's the amount of spring potential energy that gets released when the spring expands. And the spring potential energy that gets released is going to be the difference between this final spring potential energy and the initial spring potential energy. Finally, the spring will be uncompressed. So X is 0. Initially, we're told the spring was compressed. It was compressed by 2 centimeters. So with this little equation here, the relationship between the work that's done by the spring force and the stored spring potential energy that gets released in terms of the spring constant and the compression of the spring, I can figure out the work that's done. So I fill in the spring constant. I fill in the initial and final compression of the spring, and I get the energy that's released. Just 1/10 of a joule in this case. So now I know the work that's done by the spring force. I can use that work that's done by the spring force to figure out the net force, the net work that's done, and it's simply spring forces work that's done, because as we said, there was no work done by gravity, no work done by the normal force. And that determines the change in kinetic energy, which in this case, since the object starts from rest, is the final kinetic energy. And so this equation here, I can simply rearrange it. I want to figure out the final speed. I know the work that's done by the spring force. I can rearrange it for the final speed in terms of the work that's done by the spring force. All I need to do is multiply by 2, divide by the mass, take the square root. I can fill in the 0.1 joule of energy work that is done by the spring force. I can fill in the mass of the block itself, and I get the final speed. And so that's another example of the sort of energy perspective, this new, modern, innovative perspective in understanding, explaining the motion of objects that supplements the force perspective. Okay, let me finish there. In the next class, we're going to talk more about these different forms of energy, and in particular, we're going to talk a lot about energy conservation and different applications of energy conservation. So if you've got any questions, I'll stay on Zoom and try and answer those. If you've got any questions, more questions about the test, you can ask them feel free to answer them on Zoom.